This is the electrical switchboard for a vessel I served upon. From the top, we see a synchronoscope, a voltmeter, an amp meter, synchronizing lamps, a frequency meter, a watt meter, and a series of controls to run the diesel engines to keep the lights on in the ship. That is the goal of this class. We need to go from zero knowledge of electricity to understanding everything that's on this switchboard in one semester. We will base this course on the textbook by Alan Hambley. That's Electrical Engineering Principles and Applications, 7th edition. My name is Aaron Dahlin, and it's my pleasure to be your instructor. Shall we begin? We start with a class outline. We are going to start with direct current. That's approximately Chapter 1 and Chapter 2. From there, we'll have an exam. We'll move to AC, and then we'll have an exam. By the way, that's chapters 3, 4, and about half of 5. From there, we move to power and 3-phase. And we'll have an exam, which brings us to electrical machines. And one more exam. Okay, now that our calculator is fixed, let's start at the beginning. If you were in the lab, I would have given you a battery and this LED. And I would have asked you to figure out if you can light it. And what you would have done is you would have taken the LED, oops, not dropped it, taken the LED, you would have connected up one way, and you would have said, well, it doesn't work that way. Then maybe you connect it up the other way, and there it does work. And from that, you would drive up some knowledge. You would say that the LED must have some kind of directional attribute to it, as does the battery. And perhaps you already knew that. Because a battery has terminals. We have a positive terminal and we have a negative terminal. If we were to draw that as a schematic, we would say we have the battery, we have a switch, a resistor, and we have the LED, all forming a circuit. So we have the battery, the switch, a resistor, and the light emitting diode. And we made some statements about the polarity, and we said that current, or we would say current, will only flow in one direction. And you might draw that on the schematic like this, where we would say that the current flows in a circle. One way to think about current is to take a piece of wire and we establish an observer. That observer will look at the particles that flow in this wire. And we could say that the current in that wire is, we'll call the particles electrons for now, is electrons per second. Or if you wanted to use calculus, you could say that I of t is dq, which is the charge, again the number of electrons, per unit time. Some interesting implications here. That means that current can change as a function of time, which we'll get into momentarily. I'm going to do a little bit of mind mapping here. So we talk about current. Okay, current as a thing. And we would describe current as a flow of charge. We talked about electrons per second. And we mentioned with our calculus, if we so choose, we could talk about it as dq dt. We'll move on here, and we'll moving on, we would say there are two kinds of current. There is a direct current, all right, so there's a direct current, and some of its properties, it flows in a single direction. There's a concept of polarity, and that we saw with the battery when we talked about the terminals. There's a positive terminal and there's a negative terminal. We saw that single direction when the LED would only light one way. See, it's not lit there. If we flip it around, it does light. Okay. Oh, and we could also describe this as steady or unchanging. If you were to graph it, right? If you were to graph a direct current, if this was your 0, you might describe this as maybe 2 amperes. Kind of a boring signal. It's just straight and flat. The other thing is that accounts for about the first quarter of the class. The other kind of current is alternating current. So we come off here. There are 2 types of current. The other one is alternating current. And we call that AC. Should have mentioned this. We call direct current DC. Our alternating current changes with time. It has a frequency. And it has a period. If we were to graph it, you might see something like this, where you have a sinusoidal signal that changes as a function of time. And that will be the middle, about half of our class. This particular class, if you recall, has a prerequisite of precalculus. And the reason it does that is because you need to know those trigonometry principles. For example, if I told you to plot I of t is equal to 2 cosine of 377t, you would say something like, well, this here must be an amplitude. And this must be something about frequency. Actually, angular frequency. You may recall that this here, this term right here, is omega. And we describe, not a W, but omega, is equal to 377 rads, so radians per second. You may remember that omega is equal to 2 pi f, where f is the frequency in hertz. Okay, so 377 is equal to 2 pi f. Turns out that f is equal to 60 hertz, which is the frequency of your power line. By the way, while we're here, why don't you go ahead and put that down on your note card. You're going to be using that one from time to time in the class. All right, where were we? Frequency is equal to 1 over the period, or 1 over time. Okay, so again, this was frequency. And this is the period. So finally, we arrive at F. Oops, wrong color. So our F in this case is 1 over, correction, our time in this case is 1 over F, which is 1 over 60, which gives us 16.7 milliseconds. Hold on, I'll come back to the milliseconds in a moment. And now we can graph this out. And did we say cosine or sine? We said cosine. We said cosine. So our amplitude goes from 2 to -2, and because it's cosine, we're going to start here. We'll go like so, come down, up. There we go. So there's one period, and in that one period, it took us 16.7 milliseconds. If I'm going a bit fast, don't worry. We'll come back to this trigonometry stuff in a later part of the class. In your book, there is a table of prefixes. You're going to want to commit these to memory. We have giga, which has a prefix of G. So that's 10 to the 9. Excuse me, my digitizer doesn't work up there. We have giga, prefix G, which is 10 to the 9. Mega, with an M, 10 to the 6th. Kilo, lowercase k, 10 to the 3rd. The unit itself, 10 to the 0. Milli, so now we're getting smaller. Lowercase m, not to be confused with uppercase M, 10 to the -3. Micro, whoops. The mu, 10 to the -6. And finally, pico, P, which is 10 to the -12. Now, this is something you're going to want to commit to memory. Okay? Memorize those prefixes because we're going to use them again and again. In the previous example, we said that the period, I believe it was the period, was 0.016 seconds. Or another way of saying that is this is 16 milliseconds. So we just move that decimal place over, 1, 2, 3. By the way, with engineering notation, you'll know that this number here has to be between 1 and 999. By the way, if you have your calculator can do some of this for you if you forget. For example, if you were to enter 0.016 into your calculator, and, whoops, 0.016 equals, there we go. And then you push the engineering button right here. It'll put in engineering notation for you. So it's 16 times 10 to the -3, which we call 16 milliseconds. Back to our direct current. We mentioned the concept of polarity. So let's go back and explore that a little bit more. There we go. Now we can see it. So the two bars are for DC, and if we shifted modes, you see the squiggly line there? That would be for alternating current. So we want to set this up to measure direct current. And we bring the two probes to our battery, and we measure like so. And we'd record that as 9.4 volts. If we were to switch it around, we would record it as a negative 9.41 volts. So when we talk about voltage, there must be some reference to something else. Let's see what that looks like schematically. So we start out with our battery. By the way, schematically, the large bar on top is for the positive polarity. You could also put a little plus here if that helps. We had our voltmeter here, and we connected one lead up there, and we connected one lead there. And the voltmeter measured a positive voltage when we had it one direction. Right, so here we have positive. And if you flip the battery around, it will read a negative. Okay. If you wanted to look at that a different way, you could say this was our original connection. Here we're drawing the battery as a circle with a plus and minus. We call that 9 volts. And this circle with a V in it is our voltmeter. And what we did is when we flipped things around, we took these wires and we made this one go here, and we took this one and made it go down there. So depending, right, so this here gave us a positive reading, and this gave us a negative reading. And we have to be careful of this, because again, it matters. It matters very much where we put this probe as far as which way the polarity is going to be. So what we've done, what we'll use to fix that is something called double subscript. So double subscript. And it goes like this. If we're given an element, okay, given an element, we don't know what the element is. It might be the battery. It might be a resistor. I have one around here somewhere. Right? So here it might be a resistive load like that. Or it could be a light bulb or the computer. But given an element, we talk about the current passing through and the voltage across. So here is an element. We're going to label the points A and B, and we're going to say this is 9 volts. And you're going to read this. So read as voltage at point A with respect to point B. Okay, so we would say there is 9 volts A with respect to B. So we take our positive probe and we say that's the positive terminal. And we say with respect to B, we get 9 volts. Current is also involved here. So we might have a current here. We'll call it 2 amps. And what we would say is that we read this as current in the direction of A to B. So read as current in the direction of point A to B. Sorry, my big head's in the way. So that current is read as the current in the direction of point A to B, whereas the voltage is read with, where the voltage is read from point A with respect of B. So one, we're talking about the flow through. Another, we're talking about the voltage across. Right? Current through in a specific direction, and voltage in across, and voltage across 2 particular points. If you wanted to look at this another way, we could say the battery voltage A to B is equal to 9 volts, and the voltage B to A is equal to negative 9 volts. Again, it just matters which way you put the probes on your source. We'll talk more about voltage and current in the next class. For now, just think of voltage as a force or a field which gives rise to a current. If you wanted a water analogy, you could think of voltage as the pump, which moves everything along. New topic, and that is Ohm's law and the power law. So Ohm's law and the power. And it goes something like this. We have E, I, R, and over here we have P, I, E. Maybe do that a little bit neater. Well, we tried. We have E, which is the voltage, units of volts with a symbol of V. We have I, which is the intensity of the current, with units of amperes, which we abbreviate as A. We have power with units of watts, symbol W, or the units is W for watts. And finally, we have resistance, with the units of ohms, abbreviation omega symbol. Now, Ohm's law describes the relationship. It describes a relationship between voltage, current, and power. When you're just starting, it's good to have these symbols here. And what I'm going to show you is called the cover-up method. So if you wanted to calculate the voltage, you would cover up the voltage and you would say, well, voltage is a current times a resistance. And we can write that over here. We could say that voltage is equal to a current by a resistance. We could calculate the current, cover that up, and that's a voltage divided by a resistance. Or the resistance, which is a voltage divided by current. We can do the exact same thing for power. So P, I, E. There we go. So there's pi. And we do the same thing. We cover up P. So power is a current times a voltage. And you could do the rest again with the cover-up method. And E, again, so E is a power divided by a current. If you were to take and do some algebraic manipulation, you would also find that power is equal to the voltage squared divided by resistance, and it's the current squared multiplied by the resistance. And you'll find that these are particularly useful as we go along. With them, you don't have to do two steps in some of the problems. Let's see how this all works with a real problem. We'll assume a 24-volt power supply. We'll put in a current meter. We'll have a switch, but we'll assume that switch has been closed. And then we have a 2 ohm resistor. So 2 ohms. And if you'd like, we can put a voltmeter out here for good measure. By the way, a resistor converts electrical energy into heat. A resistor is a heater. How about that? We could talk about the voltage source as the source of power, and again, the resistor is converting that into heat. Let's do some calculations. So one of the things you might want to know is what is the current that flows through here? Or another way of saying that is, what would this amp meter read? So I is equal to a voltage divided by resistance. In this case, it's 24 divided by 2, so it's 12 amps. And I think those are the three things we could know from Ohm's law. Okay, we know what power is, or excuse me, voltage. We said that was 24 volts. Our resistance was 2 ohms. And because of that, our current will be 12 amps. We can work on power at this point. We could say power is a product of the voltage and current. So that's 24 times 12, which is approximately 290 watts. We could use those other formulas as well. We could say power is equal to voltage squared divided by resistance. So what is our voltage? That's 24 squared divided by 2. Let's try out our calculator here, see if that's true. So 24 squared divided by 2. Yep, so that's approximately 290 watts. We could also say that power is equal to I squared R, which is current, 12 amps. 12 squared multiplied by 2, and that's 144 times 2, which is about 290 watts again. And you'll notice it didn't matter which calculation we used. It was always 290 watts. You could say that 290 watts was provided by the source, and about 290 watts was consumed or dissipated by that resistor. Your author at this point talks about the passive sign reference. So passive reference. And I would like you to consider two elements. So we'll let this be A and B, and we'll let this be 10 volts DC. Now, do you remember what that meant? So that means voltage A with respect to V reads positive 10 volts. Let's assume there's a current flowing here of 2 amps. Okay. Now here's our other element. Again, it doesn't matter if it's a battery or a resistor at this point. A, B, and we'll let this be 10 volts DC. Okay, so both elements are the same at this point. But this time, we're going to let the current flow in the opposite direction of 2 amps. Now, we know that power is equal to IE. So in both cases, it's 20 watts. We've got to be careful, though, because one of these elements is charging or absorbing energy, and the other is supplying energy. We've got to watch out to see which one's which. In this particular example, we see that the current is flowing in the direction of A to B, and the voltage is measured A with respect to B. When that happens, we consider this to be absorbing. And the sign, as far as energy is concerned, is positive. You could think of this as absorbing energy. Over here, we have voltage A with respect to B is 10 volts, but the current is flowing in the direction of B to A, which is just the opposite. So this here, you could think of this as supplying energy. And we would say that the sign associated with this is negative, as we are losing energy. If it helps, you could look at this another way. Suppose we had a power supply that was used to charge a battery. Now we'll put a voltmeter in between the two, and because they're connected with ideal wires, they'll share the same voltage, and we'll call that 10 volts DC. If we assume there's a current flow in this direction, we can see that one of these is supplying energy and the other is absorbing. Again, going back to our references, if we have a voltage A with respect to B, and there's a current flowing in the direction of A to B, we call that absorbing. You could think of that as the load. Whereas over here, if you have a voltage A measured with respect to B, and you have a current flowing in the direction of B to A, you could call that a supply or a battery if it helps. One more topic, and then we'll be done with our marathon lecture. Energy. Is equal to the product of power and time. If we were in calculus, we would say that the energy is equal to the time integral from time 1 to time 2 of the power dt. Now, something to note, if power is constant, this simplifies back to what we originally had, where we said that energy is equal to power times time. In our earlier example, we said that power was approximately equal to 290 watts. Great. We might want to know how much energy is consumed in, say, 3 days. So find energy in 3 days. How much energy is consumed in 3 days? So energy is equal to power multiplied by time is equal to power, and we said that was about 290 watts, by 3 times 24 hours. So we have 3 days, 24 hours in each day, which gives us about 21 kilowatt hours. So here's the units. We have watts and hours. Again, there are other measures of energy, such as BTUs and horsepower hours, excuse me. But for now, we'll just stay with our kilowatt hours as a unit of energy. By the way, that is how you purchase electricity. So if we let electricity cost 13 cents per kilowatt hour, we would say 21 kilowatt hours, do some dimensional analysis here, so 0.13 by kilowatt hours, gives us about $2.73 to run that load for 3 days. What do we got left here? Oh, one more. One of the homework problems you're going to be asked to do asks about the energy in a battery. So suppose you have a large lead-acid battery. So we'll have some terminals up here with a plus and the minus. We'll let this be a 6-volt, 250 amp hour battery. That's a pretty big battery. That's about 61 pounds. Heavy battery. Replaced a few of them over the years. And what you want to know is how long can this battery supply a 2 amp load? So how long for a 2 amp load? Something you need to know about batteries, and that is that the capacity of a battery is the product of current and time. But you already knew that, because right here, when we talked about the battery in terms of amp hours, again, it's a current and a time, product of current and time. So if our capacity is 250 amp hours and our current is 2 amps, we can find time as about 125 hours. Again, that's similar to problem number 30 on your homework. On a related note, you might want to know the energy contained in the battery. So the energy contained in the battery. And we said that energy is the product of power and time. So the energy is equal to I E. You can do that, right? Because power is the product of current and voltage by time. And from our example, we knew that current was 2, voltage was 6, and we had 125 hours. So that is equal to 1.5 kWh. It might have been easier. We'll put an or here, right? So here's another way of looking at it. You could have said that energy is equal to 250 amp hours by 6 volts. Is that cheating? Let's look at this. So here we have amp hours, which is here, current, and time. So we put those two together. And we said energy is amp hours by voltage, which works out to the same thing, about 1.5 kilowatt hours. Done. So yes, the lecture is fairly quick in this class. However, I want to point something out to you folks. So consider this. Consider we have a building and we need to hold the roof up. And we've got some pillars that we rest upon. So one of the pillars is the lecture. That's not going to hold the building up. From the lecture, you have the peer time, which is a collaborative thing that you'll do with your classmates. You have homework. I will be available for a study hall. I'll post that schedule in our Teams place. From there, we also have labs. And finally, you have the last pillar, which are the quizzes and the exams. So that's a lot of things holding up this building. So don't get too frustrated if you don't understand all the material. By the time you get to the peer time and by the time you get to the homework, you should be in much better shape. If you still have problems, that's when you start asking me questions or ask your classmates questions. We get to the labs, that will help a little bit as well. And then all of that is done before you get to the quizzes and the exams. All right. Let's do a quick review before we close. So we talked about AC, and we mentioned that we're going to come back to that later. For now, you might want to write this equation down, that omega is equal to 2 pi f. And from your trigonometry, you shouldn't have too many problems getting to the point where you can plot out either a sinusoid or a cosine wave. We talked about these prefixes, and you must memorize them because we're going to use them again and again. We briefly talked about engineering notation, where the first number should be between 1 and 999. We mentioned your calculator will take care of some of that for you. For example, if you had 1.2 megawatts, right? So it looks something like that. No, that's not megawatts. That's gigawatts. If you hit the engineering button, there we go. That's 10 to the 9. So that's 1.2 gigawatts. That might help. Again, remember the engineering button on your calculator. What else? We talked about polarity and the fact that it matters which way you connect up your probes. Let's see. We talked about voltage measured across. So we had voltage A measured with respect to voltage B. And we talked about current flowing from flowing in the direction of A to B. That was useful. Ohm's law and power laws. Yep, commit those to memory. Commit all of this here to memory. You're going to use it again and again and again. We had a circuit where we examined the relationship between those three elements. So we used Ohm's law. Right there was one form of it. We also used the power laws. And we determined that we could use multiple ways and come up with the same answer. Some ways are faster than others. Some ways you can do it in one step. Sometimes it takes two. The passive reference, again, we talked about this multiple times. If we have voltage A measured with respect to B, and that current is flowing in the direction of A to B, we would say that that element is absorbing power. You could think of it as a load. On the other hand, if we have a voltage A measured with respect to B and a current flowing in the direction of B to A, we would say that that is a supplying. And the sign associated with the supply is negative because it's losing energy. Next, we talk about energy as the product of power and time. Again, you can play some games of calculus if you like. If power was constant, it didn't matter because energy was just power times time. This is useful, that example, to figure out how much energy is consumed over a particular period of time. And that might be used to determine the cost. From there, we talked about the battery, and we gave an example of a 6-volt battery. We determined, or excuse me, we stated that the capacity of the battery was measured in current times time, or units of amp hours. From there, you're able to figure out energy, and you could do that by this equation here, or you could have remembered that this is also true, that amp hours times voltage will give you energy. And then here was the plea not to get too frustrated with this class. Ask lots of questions and be safe out there.